Okay, topic 2 in our investigation of chemical kinetics is going to be a way that we describe the way a reaction proceeds, because what you're used to so far is actually a pretty oversimplified version of the way the reaction actually proceeds. So we're used to right now looking at chemical reactions, these things that you balance, okay? That's a very oversimplified representation of what actually is happening, okay? Just the idea that A plus B goes to make C is actually a lot of the times way too simple. And what actually goes on is this reaction can be described in what we call a mechanism. And what a mechanism is it's a series of what looks like a chemical reaction, but it actually displays what actually happens to make a reaction take place. And what these are going to feature would be what we call elementary steps. And that's an individual step within the mechanism. The one I'm getting ready to show you is actually just a two-step mechanism, so a mechanism with two elementary steps. It's not uncommon to see these things with three, maybe four elementary steps, and I'm sure that there's ones with many more steps than just three or four, but that's about where the College Board will stop with what they put on the AP exam. So the first thing is really a vocab term, and that's what we call the molecularity of a specific elementary step. And simply what I'm talking about with molecularity is how many reactants are in a specific elementary step. And there's going to be a slide over that in just a second. And then the second vocab term that I want to talk about with this slide here is what we call an intermediate. And these are things that are produced. And these are the things that you would never see in a normal chemical reaction, things that to your knowledge doesn't even exist. And the only way we can ever even see the existence of an intermediate is if we have a reaction mechanism. So these are things that are simply produced and then quickly reconsumed in the next elementary step. There's methods that we were going to look at in class that will allow us to get to the balanced chemical reaction from the mechanism, and that's something that I'll save for actually in class. So when talking about molecularity, we have some vocab terms, unimolecular, bimolecular, and termolecular. And all that is telling us is how many reactants are in a specific elementary step of a mechanism. So if we see just one substance or one reactant, we would call that elementary step a unimolecular elementary step. If we have two reactants in an elementary step, we get a bimolecular step. And then finally, termolecular represents a three reactant elementary step. So a very useful tool with these elementary steps. Now, again, we've not yet seen a mechanism. We will on the next slide. These are simply examples of elementary steps, things that could be part of the 1, 2, or 3-step mechanism. But I've put these here to show you guys, first of all, what we would call these elementary steps. So, for example, let me get my pen here. The top one is a unimolecular elementary step, as we just have one reactant. Here we get a bimolecular elementary step, and actually we get a bimolecular step in the third one as well. And these final two are a termolecular elementary step. Both of those are examples of termolecular. Now, the main thing here and the usefulness of these elementary steps is we can actually write a rate law of an elementary step. So far we've just seen rate laws of the overall reaction, but here we actually get a way to describe a elementary step with a rate law. Now I want you to take a look at all that happens here. We're simply going to take the reactant and we're going to move it into a rate law, and simply all we do is however many of these reactants we have, that is the exponent or the value of m or n that we saw in the previous video. Now take a look at what happens when we get a bimolecular elementary step. We have two identical reactants here, so we're just simply going to put those into one term, but notice how we've got that squared now. When we get two separate reactants, we set up two separate terms here. Once again, there's only one of each of these in the reactant side here, so our exponents are just one for those. We can see a similar scenario happens here when we have the multiple of reactant B. We square that, but just one of reactant A, and then finally you get the idea here with the last one. Now, the main idea that I want you to take away from this is it tells you the reaction order for the elementary step. Notice unimolecular corresponds with a reaction order of 1. Remember, this is where we sum the exponents in the rate law. That's what I mean by reaction order. So for a unimolecular step, 1 plus nothing gives us 1. For a bimolecular reaction, we get a reaction order of 2. Another bimolecular, 1 plus 1 gives us 2. Termolecular, we get a reaction order of 3. So what I want you to take away from this is a unimolecular reaction corresponds to first order. Bimolecular corresponds to second, and then finally termolecular, the overall reaction order is third. Now that's pretty useful because when we get these elementary steps that we can write rate laws from, we can quickly determine the overall reaction order from those. So here we see an example of our first mechanism. Okay, so what we notice here is that we have two different elementary steps. We have a bimolecular, elementary step up here, and another bimolecular elementary step here. Now, the useful skill with this is here's how we're going to get the overall reaction. So what I want you to do is anything that appears identical but on opposite sides of the arrow. So for example, this compound here that doesn't really have a name, Br2NO, that appears identical on both sides. So we can absolutely get rid of that. And that's what we call an intermediate. That's something that you never know existed before, and it's something that is produced in one elementary step and then quickly consumed in the next one. So it's kind of just something that helps us to go ahead and form the desired product. So once we're at a point where we can cancel nothing else out, what we do is we simply add up the reactions. All right, everything on the left side or the reactant side gets put on the reactant side of the final answer, and then everything that's left on the product side gets put on the product side of the final answer. So I'm just going to go ahead and copy everything down here. I'm not going to include my states because I'm going to run out of room. Now here we see an example where we have two NOs. It is standard practice to just go ahead and write that like this and not to write NO plus NO. All right, so we don't want to do this. If we can combine it, that's what we want to do. So now we're ready for our reaction arrow, and the only thing on the product side up there is just BRNO. Now what we're going to notice here is we have determined the balanced chemical equation. So as I mentioned earlier, you can get the balanced chemical equation from the mechanism simply by canceling out things that appear identical on both sides or on opposite sides of the reaction arrow. And if we check, we're going to be totally balanced here. We've got two BRs on this side, and we get 2 on this side. We get 2 nitrogens on this side, and here are our 2 nitrogens there, and then finally 2 O's and 2 O's. So this is a completely balanced reaction, and that's how we're able to balance these things from the mechanism. Now, the last thing I want to talk about on this particular video today is what we call the rate determining step. Basically, the old adage, you're only as strong as your weakest link. The reaction is only as fast as its slowest elementary step, if that makes sense. We can only go as fast as our slowest step allows us to go. So what we call that slowest step is the rate determining step. So what we get here is the author of a specific problem will actually tell us what the rate determining step is. And by telling us that, we can actually come up with the overall rate law. because I showed you how we can come up with the overall rate law of an elementary step, but what we can actually get, and the most useful thing, is we can get the rate law of the reaction if we know what the elementary step is that is our rate determining step. So as this particular bullet point indicates, let's say the author of the question tells us that the rate determining step is the second step, or step 2. What that automatically tells us is a bunch of information. So first of all, the first thing it tells us is we can write the rate law for this reaction. Rate's going to equal K times the concentration of Br2NO times the concentration of NO. Now, that is how it would appear, but you got to be careful on these, because on the previous slide we determined that Br2NO is an intermediate. Intermediate meaning we can cross it out. And what we have to do, if we look up here, is ignore intermediates. So what we need to do is we have to get rid of that. Now that is our correct rate law. So you got to make sure that you get rid of intermediates first. Now what this tells us then is a few things. First of all, it tells us that NO is a first order reactant, and that tells us that if we double the concentration of that, the rate doubles. But it also tells us that the overall reaction order is first order. So I want you to think about what this actually replaces for us. If you go back to the method of initial rates, that's a time-consuming process. If we get a mechanism, we can now come up with the rate law in less than half the time it took us using the method of initial rates. So this ends up being a very useful step for us.